Okay, so now we've covered a couple of plot types. Now we'll look at some measures for describing our data set with just one or two numbers. The goal of having these descriptive statistics, these one or two numbers that describe our data set, are basically because we want to, in most cases, we want to summarize our data. We don't want to fill our paper with tables and tables of data. We want to say the average height is this much, the average wealth is this much, the spread in the income is this much, just single numbers that we can draw a conclusion from. And the characteristics that we will develop for our data are typically, in this course at least, centered around what is the typical value in my data set, what do I expect, how do the data vary, but then also is the distribution of data symmetrical around the typical value or not. So if I make my histogram, will my histogram look as follows? Will I have a histogram that looks like this, symmetrical? Or will I rather have something with a tail like this, or a tail like that, which are not symmetrical? And then if we have multiple variables, and if we observe that one variable and another variable are associated, we'll want to quantify the strength of that association. So let's start with the easiest measure of the typical value. Or let's start with the easiest measure to summarize what the data look like. And let's go look for a typical value of our data set. So what we want to do is we want to take our n observations, for example, our 38 sulfate levels, and we want to summarize that, and we want to get one typical value out. And I put typical in quotation marks because depending on how you interpret that is of course going to give you a different measure. And some of these ways of summarizing your data into a typical value you have already covered in high school, or you have already covered in other courses when you had to do this kind of summarization. What you probably already know about is summarizing your data into a mean or average value, and summarizing your data into the median. So we'll very briefly look at both of these in turn, and then we'll also cover the so-called geometric mean. That is a measure that is not so well known, that has certain advantages. That's why we cover it as well. But these three will always be available to you. They'll be slightly different or widely different, and I'll talk about when that happens. But these are the three most common ways to compare. And just as an example here, if we take the sulfate concentration of our 38 watersheds, and if we summarize them if we calculate the mean, we will get 62.08 micromolars per liter. The median will be 62.10, and then the geometric mean will be 61.87. We will not cover the modes, so you can ignore that for now. And what you see here is that these values are all very close together. And this is a consequence of the fact that the distribution of sulfate is nicely symmetric, but that's not always the case. We will see some examples, for example, the chloride variable, where that will not be the case. So this is not always the case. All right, how do you compute the mean or the mathematical average? I am convinced you already know how to do that. You take your observations, you take your sulfate levels, you add them together, and you divide by n, by the number of observations that you have. We typically denote that by x bar. The bar indicates we take the average of the entries. And in mathematical notation, with the big sigma, the sum, you can express it like this. A couple of examples here on the slide. If I take the mean of 1, 2, 3, 4, 5, 6, then what do I have? Well, very easy. 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. That is 7 plus 7 plus 7. 21 divided by 6. That is 3.5. We already covered the mean concentration of sulfate. We saw that it was 62.08 micromolars per liter. How did I obtain that number? Well, I just loaded the data into R and then asked it to compute the mean. I'm not going to add 38 numbers and make you sit through that. Just use the computer or your calculator for that. And then a funny but very revealing example to show you how the mean can be a good and sometimes not so good measure to consider. Comes from a study by Miller and Fishkin that's now about 30 years of age. And in this study, Miller and Fishkin did a survey and they asked men and women, I assume young men and women, they asked them for their mean, for the desired number of romantic partners over the next 30 years. So just asked a bunch of people, men and women, how many partners do you think you will have or would you like to have over the next 30 years? And I can imagine that most people said 1, maybe 2, 3. And those would be my guesses for typical values. But now if you look at the mean number of desired partners for men versus women, then you see some really weird numbers. So women report on average desiring a number of 2.8 partners over the next 30 years. And that's a number that I can get behind. That's 1, 2, 3, 4 maybe. But if we look at the number for men, then we see men report desired number of partners to be on average 64, and that's a very strange number. It probably, if you're a boy listening to this lecture, probably does not correspond to what you would respond in this survey. And if you're a girl listening to this lecture, then you would probably also think like, is this really the desired number of partners that men report on average? Before you draw any conclusions about men versus women from this number, I would like you to suspend your thinking for a little bit, and I would like to indicate that this makes the mean sometimes into a very skewed measure of the typical. So mean is sometimes very skewed. And what that means, I will explain in the next or in what comes after. Before we dive more into why the mean is skewed, let's first talk about the median. Let's compute the median. So the median is the 50th percentile in your data set. What does that mean? It means your median is the number such that half of the observations in your data set are larger or equal to that number, and half are smaller or equal to that number. So now, how do you compute the median? A very straightforward procedure. First step is you sort your data, and then the second step is basically you're going to choose the middle value of that sorted data. And there's two cases to consider. if you have an odd number of observations or an odd number of data points, then you're really going to choose the center value, the middle value in your sorted sequence. If you have an even number of data points, then you can't choose the middle value, because if there's even, then there's no middle one. Then you're going to take the middle two, and you're going to take the average of both. So let's see that in action on a couple of examples. So here first, let's compute the median of 1, 2, 3, 4, 5, 6. So step one is we're going to sort those values from smallest to largest. It's already sorted: 1, 2, 3, 4, 5, 6. And now we're going to choose the middle value. We have 6 values, so that's an even number. So we have to take the middle 2, 3 and 4, and we have to compute the average of those two. 3 plus 4 divided by 2 gives me 3.5. So here the median of 1, 2, 3, 4, 5, 6 equals 3.5, just like the median, just like the mean. So the mean was also equal to 3.5. Now let's do the second example, 1, 2, 3, 4, 60. Again, we sort the data. It's already sorted: 1, 2, 3, 4, and then 60. And that's 5 observations. That's an odd number. What is the median? The median is 3 here. So the median here also is equal to 3. Now let's go and look for the mean. And for the mean, what do we have to do? Well, we have to sum all the values together. And we have to divide by the number of observations, which is 5. And that equals to exactly 14. If you do this with calculator, you'll find 14. So the mean here is 14. And we're going to come back to that in just a second. Let's first work through the other examples as well. If we compute the median concentration of sulfate, we get 62.10. That's computed with R. And then if we look at the median of the desired number of partners for both men and women, then we find that the median is not some high number like 64, like it was for the mean, but we see 1. So both for men and for women, the median number of partners is 1. And so now that sort of raises a couple of questions to us. We see that there's some examples like sulfate where the mean and the median are very close together. And we already said that happens sometimes. This happens when your distribution is symmetric, but it doesn't always happen. How come that it doesn't happen? Well, in order to understand when the mean and the median are different, you can look again at this second example that we have here. In the second example, median of 1, 2, 3, 4, 60, then what makes this example special is that you have one very large observation, this 60 here. And let's have a look now at the computation of the median. We have that 60 here in my sorted list. And you can see that the fact that it's 60 doesn't influence the median at all. If this was 600, the median would still be 3. And if it was 6, the median would also be equal to 3. The only thing that matters is that that 60 is bigger than everything that came before it, 1, 2, 3, 4. So what you see is that the median is robust to outliers. That 60, that is an atypical value, that is, we could call it an outlier, a very extreme value. But the value of the median does not depend on that outlier. We say that the median is robust to the outlier. But if we look now at computation of the mean, then you see the mean takes into account all of the data. In particular, it takes into account the value of this 60 in my computation here. If I turn this 60 into a 6, the mean is going to go down. If I turn my 60 into 600, the mean is going to go up even more. So even though the 60 can be considered to be an extreme value or an outlier, the mean will sense that outlier. The mean will depend in some way on the value of that outlier. And actually, we will see that the same is true for the example of the desired number of partners. There are a couple of outliers in the data set, and because of that, the mean number of desired partners is skewed towards those outliers. It senses those outliers. But if we compute the median, then we have the typical value minus the outliers, and that's why we have a median value that is much more close to what we expect. Before we unpack that a little bit further, I want to point out, as it says on the bottom of the slide, that the median also makes sense for censored data. What is censored data? Censored data is data where you have some observations and then also some labels that tell you something about the data point without giving you a value. For example, let's say that we do a chemotherapy study on lab animals. We give them some tumor and then we treat the animals. And we run our study for 12 weeks. And in that 12 weeks, we monitor day by day, or week by week rather, whether the animal is still alive or not. And we record the week in which the animal dies. And let's say that we have 6 animals in our study, and we observe for the first 4 animals that animal 1 dies after 1 week, animal 2 dies after 3 weeks, animal 3 after 4 weeks, animal 4 after 7 weeks. And now let's say that the last 2 animals, 5 and 6, they survive the entire study. Then we cannot write down what their lifetime would be because our study stops after 12 weeks. The only thing that we can say is that their lifetime is bigger than 12 weeks. So in this case, we have to record lifetime bigger than 12, bigger than 12. This is censored data. We don't know the exact lifetime of the lab animal. The only thing that we can say is that its lifetime is bigger than 12 weeks. Even though we don't know the exact lifetime, we can still compute the median lifetime of the animals. Why? Because we can sort this data set. We can say 1 is less than 3, is less than 4, is less than 7. And then what do we do with bigger than 12 and bigger than 12? Well, we don't know what those are, but bigger than 12 is definitely bigger than 7. So we have bigger than 12, bigger than 12. And it doesn't matter whether rat 5 lives longer than rat 6 or the other way around. Those are just extreme values. What matters is that both of them are bigger than the value that precedes it, 7. Now, how do we find the mean from this sorted set of data points? Well, I have to take the middle 2 observations because I have 6 observations, and those middle 2 observations are 4 and 7. 4 plus 7 divided by 2, that is 11 divided by 2, that is 5.5. So here the median lifetime is 5.5 weeks. Let's take another look at the study from Miller and Fishkin. So here you have a bar plot. It's a scan from a book, so it's not very easy to look at. But the light blue bars are men and the dark blue bars are women. On the x-axis, you have the desired number of partners. And then on the y-axis, you have the number of people that reported wanting to have that many partners. And actually, rather than the count, how many, it's the frequency. What percentage of men versus women said, I want 0, 1, 2, 3, 4, 5, and so on, partners. Now, if you look at this bar plot, then you see the highest bars here are for 1. So this is very intuitive conclusion to draw from this plot. Most men and most women report in the study, I would like to have one partner for the next 30 years. There's a few people that say, I'd rather be alone. I want 0 partners. That is also something that we can understand. And then we have a small range here from 0 to 5, 6, where people say, well, okay, 2 partners, 3 partners, 4 partners, that is the number for me. I'm not going to draw any conclusions from that, but these are all values that shouldn't raise any eyebrows. Well, now let's have a look at the extreme tail end of this distribution. We have some people here that fall in this bucket that report, yeah, I would like to have 100 to 1,000 partners, or 1,000 to 10,000 partners. So I really don't know what kind of people that those are, but in our survey we have some respondents that marked that. Probably just people that thought that they would be funny by saying like, I'm going to be like a Casanova and have 1,000 partners. But these are probably not observations we should take seriously. However, what you see is that because of these extreme observations, our mean also increases towards that extreme number. And in particular, I sort of drew over it a little bit, so I'm going to erase a little bit as well. It's not the women that are making these jokey observations. You can see a very small bar here for the men. It's the men that are making bad jokes and are saying, I want 10,000 partners. And therefore, it's the mean for the men that is skewed. The mean for the women is also skewed a little bit, but not by a lot. So here, what we see is that because of these high observations, the mean gets drawn towards those high observations. And if you compare the median is 1 for both men and women. The median does not see these extreme observations. The median sees the 50% of observations that are below it and above it, but not the exact value. So if you have to decide, do I compute the mean or the median, then you should think, do I have outliers, extreme values in my data set? Do I want those extreme values to be reflected in my summary measure? If so, then compute the mean. Or do I want a summary measure that is robust to outliers, in which case compute the median? Sometimes the mean will be better, sometimes the median will be better. For this study, the desired number of partners, I would argue the median is a better measure. That is also reflected here on the slide. Just to add one more observation here for number 2. So if you have a skewed distribution, if you have a distribution with a tail like this, a long tail to the right, then what are your mean and your median going to look like? Your median will be maybe here, median. But your mean will be attracted towards the tail, towards the more extreme values, mean. And if your distribution is skewed in the opposite sense, if it looks like this, okay, sorry, let me make that again. If it looks like this, then your median might be here. and your mean will be drawn more towards this side, to the left side of the distribution. If you have a symmetric distribution, I will add that here, so distribution that has no skew either to the left or to the right, then your mean and your median will be equal. So this happens if we have a symmetric distribution. This happens when we have left skew, and this happens when we have right skew. And then last, you can also use a transformation on your data to make it more symmetric. For example, taking a logarithm, and then if you've transformed your data, then you can again compute a summary measure, so that is also an option. And actually, yeah, this is what we have here on the slide. This is a histogram of blood pressure in a sample of obese patients. And what you see is that there is right skew in this distribution. There are some values here on the right that are more extreme than we expect. And typically in this kind of distributions, it is very common to see skew to the right. And the slide asks here, why do you think that is? And this is a very common phenomenon with natural things that are labeled by positive quantities. For example, blood pressure. Blood pressure cannot go below 0, or it cannot go below whatever the physiological lower boundary is. But your blood pressure can be very high. So it can be 180, it can be 200 milligrams or millimeters of mercury pressure. So it has a lower boundary, but no real upper boundary. Hard lower bound and no real upper bound. Every doctor will have stories. If they exchange stories, they'll say like, oh, I had a patient with 200 blood pressure. Oh, I had a patient of 250 blood pressure. No real upper bound. So here, if you were to compute the mean would be more attracted towards the higher end, whereas the median would be more reflective of the bulk of the data. Now, if you take the blood pressures and you take the natural logarithm, so if you compute log of blood pressure and now you put that in a histogram, then you see a histogram that's a little bit more symmetrical. And this is a typical thing that we see. If you have things that are skewed to the right, then try doing a logarithm try logarithm transforming the data. It will make your data more symmetric, generally speaking. And now that leads us naturally to the concept of the geometric mean. So here we have some numbers. We've already seen that blood pressure in our sample is right skewed. It has a tail to the right. It has some values that are higher than what we would expect based on the bulk of the data. And you also see that reflected in the mean and the median. The mean is 127 millimeters of mercury, and the median is only 124 millimeters of mercury. Now, if we do a log transform, and by log transform, I mean we take the logarithm, the natural logarithm of all the observations. So if our observations here are x1 through xn, then what we're going to do for this logarithm transformation is we're going to compute the logarithm of x1 through the logarithm of xn. These are new observations. And then here, this mean and the median, they refer to the logarithm transformed data. So for example, the mean log transformed data is given by 1 over n logarithm x1 plus logarithm x2 plus ... logarithm xn. That's what gives you the 4.84. Now, if you do that mean of the logarithm transform, then you get a very strange quantity. Logarithms of blood pressure and then added together. What does it mean to interpret a logarithm of a blood pressure? It's not clear to me. It's not clear to you. It's definitely not going to be clear to your doctor if you say, I have logarithm blood pressure 4. What you have to do in order to have a quantity that is physically relevant and meaningful is you have to transform back. You have to undo the effect of the logarithm. How do you undo the logarithm? You take the exponential. So we take our mean of the log transform data, that's 4.84, and we take the exponential of that. And that gives us 126.5, and now the units work out, of millimeters of mercury. If you do these 3 steps, log transforming, mean, and then exponential, then you get something that we call the geometric mean. So just to write down the formula, what is the geometric mean? It is the exponential of the mean, and we'll use the summation notation, of the logarithm transformed data. And just a matter of notation, in this course, we will always use the natural logarithm. So when I write log, then I mean the natural logarithm that you sometimes also see as ln, the natural logarithm. If I ever have to use the base 10 logarithm, then I will explicitly point it out. Now, the geometric mean has a couple of advantages. It shares some characteristics with the mean, but it also shares some characteristics with the median. Sometimes it's preferable over the median because it can be a little bit more precise. Why is it more precise than the median? If you think about it, the median throws away a lot of data. All you have to do is you have to rank your observations and then choose the middle one. But you never use the absolute values or the exact values of your data. You just say, this observation is the middle one, and I don't care what the other values are, I just want the middle one. The geometric mean and the mean actually, they use all of your data points. They use x1 through xn, the exact value. That makes the measure a little bit more precise. Now, it is more precise, but it also avoids some of the characteristics of the mean. The mean is attracted by the outliers in your data set. The geometric mean will be a little bit less attracted by the outliers. Here you can already see that the value that we obtain, the 126.5, is slightly lower than the 127 that we had from the mean. So the geometric mean sort of sits in the middle between median, completely robust to outliers, and mean, not robust at all, and therefore is a good third measure to compute. If you are wondering, which one should I compute, mean, geometric mean, median, then it's a very good idea to make a histogram of your log transformed data. If your log transformed data looks nicely symmetric like I'm drawing now, then geometric mean is probably an acceptable measure to compute. If you do the log transform and it's not symmetric, then forget about the geometric mean, just go with the median. Now, secondly, we don't always care just about the location of the data, but also about how much the data are spread around the location, how much they are spread around my central measure. And sometimes measuring the spread in the data can be the primary goal, can be the first thing that we're interested in. For example, if we're making some kind of new measuring device, like a scale or a sensor, then what we want for the sensor or the scale to be accurate and for its measures not to fluctuate too much. In that case, we will be very interested to know, if we measure an object with a standard weight, what is the spread in the measurements that we obtain. So here I can add, for example, when designing or when calibrating a measuring device. So we'll have to come up with a number that measures the spread in our data set. And there's a couple of such measures, just like there were a couple of measures of location. So first, let's go over the most common concept, so-called variance. Variance, we have the formula here on the slide, but I want to unpack the formula a little bit before. This consists of a number of things put together. So if we take a histogram of our data, then the first thing that we're going to measure is, for each data point, how far it is away from the mean. So we're going to take data point I, xi, and subtract the mean from it. If this is my mean and data point xi is here, then we're going to take xi minus xi bar. So that is how far my data point is from the mean. How far from mean. Then secondly, okay, that's going to give us how far each data point is from the mean. That's going to give us n measures of spread. We want one number, so we have to summarize those n numbers into one. How are we going to do that? First thing that you might say is like, okay, I'm going to take the average spread. So I'm going to compute this number. And actually, let me reuse what I've written down here before. I can take the average spread, sum over all I of xi minus x bar. Now, if you look at that a little bit, then you'll see that this works out to sum over the xi's, and then, oops, not 1 over n, minus 1 over n sum n times of x bar. Now this first quantity, this thing right here, that's just x bar. And then the second quantity, the x bar doesn't have a summation index I in it. So this thing right here, this is n times x bar. And together with the factor 1 over n, you see that these two terms exactly cancel each other out. So if you take the average spread, that's no good, because that's always going to give you exactly 0. What we're going to do instead is, what we care about is the magnitude of the spread, not whether it's positive or negative. So we're going to take the square. We take the square here of the spreads, and then we take the average. We sum over all the i's, and we divide by the number of observations. If you do that, then you get what we call the variance. This is the average of the squared deviations or the squared spread. One minor technical detail that you have to take into account when you calculate the variance, rather than dividing by n as you would in the mean, we're going to divide by n minus 1. Why? There's a technical statistical reason for it. It makes the variance better behaved. There's one important disadvantage that's easy to remedy. The disadvantage is you have to take into account the variance has units squared. So if your original quantity is in micromolars per liter, your variance will be in micromolars per liter squared. That makes it relatively hard to interpret what the variance means. So what are we going to do to fix that? We're going to take the square root again of the variance. That gives us the standard deviation, which now has the same units as the original observation. The next measure of spread that we're going to look at is the interquartile range, sometimes abbreviated as IQR. And what this is like a robust version of the standard deviation. Of standard deviation. And here, robust, you have to interpret that in the sense of being insensitive to outliers. And this is a bit similar to the fact that we had the mean and the median, and the mean was sensitive to outliers, whereas the median wasn't. So here too, when it comes to measure of spread, the standard deviation is sensitive to outliers and the interquartile range is not. So now, what is the interquartile range? It is the middle 50% of your data. So in other words, it is the difference between the 75th and the 25th percentile. To make that a bit more concrete, we have here on the figure, again, the histogram of the blood pressures that we already saw a few slides ago. And the blue lines are the 25th and the 75th percentile, respectively. So this one right here is the 25th percentile, and the other line is the 75th percentile. So what does that mean, 25th and the 75th percentile? Well, it's a little bit like on your transcript when they give you percentiles of the scores. The 25th percentile is the data point or the mark such that 25% of the data is lower than that value. So we have 25% of the data here. Same thing for the 75th percentile. 75th percentile is the point so that 75% of the data is lower than that value. And if 75% is lower, then of course 25%, the remaining 25% is higher than that point. And now if you look at the figure carefully, then you see between the 75th and the 25th percentile, so precisely the part that's indicated in blue, then I'm shading again, you have 50% of your data. So in a sense, the interquartile range is the middle 50% of your data set. And that tells you a little bit more about why this measure is insensitive to outliers. I could have some really high data points here or some really low data points, but the exact value of those doesn't really matter. The only thing that matters is that they're very large or very small, so that they're in the 75th or in the 25th percentile. But the middle 50% is not affected by those outliers. Now, I need to be a bit more specific here because there's a confusion that I saw on the exam a few years ago. So the interquartile range, it is a number. You have to be very careful with this. This is a number. So it's not an interval, even though it may look like that. It is the difference. You have to take this as the definition here. It's the difference between those two percentiles. So it is the length of this arrow right here, the difference between the two percentiles, it's a number. So don't write it down as an interval, write it down as a number. We go difference. Okay, so that leads us to the next visualization that we're going to look at, and that is the box plot. So I think you may have encountered box plots before in scientific papers or maybe in a bachelor thesis that you read. They're very standard visualization because they allow you to summarize an entire data set, observations of one variable, an entire data set into one plot. It's also a very information-rich plot, and understanding everything that goes on, that can be a little bit tricky. So let's unpack everything that we have here, one thing at a time. So this is a box plot for chloride. And let's start here with a big bar in the center. So this big bar will work out to about 20, 21. And the big bar is the median, or as we've seen, the 50th percentile. Now, what about the box that gives the box plot its name? So the box extends from the 25th percentile to the 75th percentile. So you can compute those, or you can read them off from the summary that we had before. And we see, yeah, probably this is about 13 and 28. Now, the size of the box, so the width of the box, that is precisely the interquartile range, because that is the difference between the 75th and the 25th percentile. So another way to put that is saying that the box contains 50% of the data. So if you look at a box plot, then you can see within a glance of a moment where 50% of the data lie. 50% of the data lie within the box. Now, that's not all. We also have these so-called whiskers. So the bars that extend, or the little gadgets that extend from the box. What are those? Well, here there's a rather complicated definition, but it's an unambiguous definition. So the whisker, the top whisker, let's start with that one, is 1.5 times the interquartile range, or the maximum of the data, whichever is lower. So for chloride, we knew that there were some really large chloride values in the range of 80. So our maximum is 80. Our interquartile range is the green arrow that I've shown you. 1.5 times that is a little bit larger. So whichever quantity is smaller, in this case, it is 1.5 times the interquartile range. So let's add that to the figure. This whisker extends 1.5 times the interquartile range. Now, for the bottom whisker, it's the same thing. It extends 1.5 times the interquartile range, or it's the minimum of the data, whichever is higher. So here our minimum was quite low. I forgot exactly what the value of the minimum was, but here we have that our lower whisker does not extend 1.5 times, is not 1.5 times IQR. That would be about this long, but it is the minimum of our data. So here we have our minimum, and here we have our maximum. So the interpretation of the whiskers, you have to be a bit careful with it. It's either 1.5 times the IQR past the box, or the maximum or the minimum of the data, but it's always the less extreme of those two values. Then the last element that we have on the figure are these dots right here. These are labeled here as outliers. What are they? Well, they are every data point that is outside the range of the whiskers. Every data point outside the whiskers. Outlier is sort of an overloaded concept in statistics. There are many different definitions of what an outlier is, but in the current context, it's the data points that are outside of the whiskers. And these could, for example, be data points where you say, I need to have a closer look to see exactly what happens. And just to run ahead to something that we will cover much more in semester 2, outliers sometimes can be physical or they can be non-physical. In this case, we have chloride values of 60, 80 micromolars per liter. From a physical perspective, these are not abnormal values. You can perfectly well have a stream with those concentrations of chloride. So these are probably streams that if you're an environmental engineer, where maybe you want to do some extra monitoring or you want to figure out why chloride is so high in those streams. But of course, you can also have outliers that are not physical. And then maybe you want to exclude those from your data set. For example, if we go back to the data set where the two researchers asked men and women about the number of partners that they would like to have in the next 30 years, then we have those people that responded 10 to 1,000 or 1,000 to 10,000. Those are outliers, but they are clearly not physical values for the research question that we're trying to investigate. So sometimes outliers are physical and you need to really study what makes them an outlier, and sometimes they are unphysical and you can consider maybe removing them from your data set. Now we've finished analyzing one variable at a time. What we're going to do now is look at two variables simultaneously. So for example, we can have a look at the concentration of sulfate and the height at which the measurement was taken. And there are several tools at our disposal for that. There's a plot type or type of plot that we can make. We can look at the correlation. That's also something that we'll do now. And you can make a regression model, but that is not something that we'll do now. We'll come back to that next semester. So first, scatter plot. I think all of you have seen this before. It's a very simple plot to make. If you have two variables, then you put one variable on the x-axis, the other variable on the y-axis, and you just you plot a single dot for each observation in your data set. So let's take, for example, this dot right here. This dot is a stream for which we have maybe, I'm just going to guess a number, 410 meters height above sea level and 56 micromolars of sulfate. So each dot in the plot represents one stream in our data set, or in general, one observation. The red line that you see on the plot, that is something that R can add for you. This red line is computed automatically by R and represents the trend in the data if there is any trend. Sometimes this is a useful visual aid to see if there's an association in the data, and sometimes if there's no trend, then the line will not tell you anything. Now let's talk a little bit more about associations between two variables. So we have here the Pearson correlation, but before we get to that, let me properly define an association between two variables? When do we talk about an association between x and y? So we say that we have an association between x and y if knowing about x gives you some info about y, or vice versa. Knowing something about y tells you something about x. And you can have a perfect association where if I tell you x, you know exactly what y is, or vice versa. And you can have an imperfect association, meaning if you know something about x, you know a little bit about y, but not everything. And the first measure that we're going to compute to quantify an association is the so-called Pearson correlation coefficient. And this expresses the linear association between two variables, with the emphasis on linear. What that means, I will make more explicit on the next slide. But for now, let's take a look at the definition. So we compute the correlation by taking the sum over all the data points and taking the spread of data point x times the spread of data point yi. So remember from the slide of the variance when we talked about the spread of a variable, we said, okay, for each data point, there's a difference between that data point and the average. So here we have spread in x, and here we have spread in y. And then we sum over all the data points, we divide by n minus 1 times standard deviation of x, standard deviation of y. And this quantity has a number of attractive properties. Let's start with the last one here. Correlation is always between -1 and +1. And it is like that because of this division by standard deviation of x times standard deviation of y. Now, if you have a positive correlation, so if your correlation coefficient is bigger than 0, what does that mean? It means that as x increases, y also increases. And a negative correlation, so when the correlation coefficient is negative, it means that when x increases, y decreases. Let's do just a very simple example of things that are positively and negatively correlated. So an example of a positive correlation could be if the temperature goes up, then also the ice cream sales go up. And a negative, so this is a positive correlation. A negative correlation could be if your expenses increase, then typically your bank balance goes down. Okay, just a few minor details about that. Even though I have drawn this arrow and I've said if this happens, then that happens, we have to be a bit careful about making that kind of conclusion. In general, the correlations that we will look at only tell you something about how these things work together. So we will not be able to say A causes B. We will only be able to say A and B are related to one another. Let's take the last example. Here I've said if your expenses go up, then your bank balance goes down. But if we compute, for example, and we find that it's a negative correlation, it could also go in the other direction, meaning if your bank balance goes down, it must be because you're spending money, hence your expenses are going up. So this arrow can go in both directions for an association. Here are a few sample data sets with their Pearson correlation, just to give you an idea of the strength of an association. Let's start with the plots on the right. So if you have correlation very close to 1 or -1, so remember the correlation coefficient, which here we abbreviate as R, has to be between -1 and +1. So if it's very close to +1, then you see the data points are almost perfectly lying on a straight line. And you can see as x increases, so x increases, y also increases. Same thing if we have if I have negative correlation very close to -1. Here we see if x increases, so if we go in this direction, then y will decrease. We will go down in the y direction. And likewise, the points are almost perfectly clustered along a straight line. Now let's go to the left. So here we have correlation 0.2, correlation -0.2. If the correlation is 0, then that means that there is no linear association between x and y. And here you can see that idea also, like it's not perfectly 0, it's 0.2, but you see that there is some association between the data, but not a very strong one. You still see if x increases, then y also increases, but it's not as pronounced as the other case. And likewise for the negative correlation here, if x increases, y decreases, but not very strongly. And there are definitely data points which defy the trend. Then lastly, here in the middle, correlation 0.7, correlation -0.7. That's a mixture of both. You have a pronounced trend in the data. For positive correlation, again, x goes up means y goes up. And then for negative correlation, x goes up means y goes down. But it's not as strong as, or it's not as pronounced as either case. You have to be very careful with the word linear in the definition of linear association. You can have a nonlinear association between two variables and still have correlation, Pearson correlation 0. So here we have a scatter plot of two variables x and y, and you can see there's a clear trend in this data. But the trend is parabolic. This is still an association, but it is not a linear association. In this case, this would be a quadratic association. In general, this is a non-linear association. And if you compute the Pearson correlation for this dataset, you'll find that R is exactly 0. So we've made it so that this dataset has very clear visual trend, but R identically equal to 0. Now the correlation, the Pearson correlation, is also sensitive to outliers in your dataset. This is something that you have to be aware of. On the left, we have a scatter plot and then a trend line. So two variables with correlation 0.98. So almost perfect correlation, very close to 1. You see indeed that very strong positive correlation. And then on the right side, we have added two new points. So the data set has stayed the same. All I've done is I've added two new points here and here that defy the trend, that are different from where the other data points lie. And as you can see, like if we ask R to draw the trend line through the data, that trend line has changed And for those of you who know, this is a linear regression line. For those of you who don't, we will see how to compute this line in semester 2. But if you compute the correlation of this new dataset with the two outliers, then you'll find that the correlation drops to 0.68, so much lower than it was before, just because you added two outliers to the data. Now, we can make scatter plots very easy in R. Actually, if you just have two variables, then you can use the plot command in R, and you will do that from now on every single practical, so I'll not cover how to make a single plot. But you can also extend the idea of making a scatter plot to having more than two variables. So here, we want to look at the association between three variables. We have the sample elevation, so how high did we take the sample, the sulfate concentration, and the chloride concentration. And what you can do with R is you can make a so-called scatter matrix. And you do that with this pairs command. And what R will do when it plots this scatter matrix is it'll take out two variables at a time and make a scatter plot for each combination of those variables. So here let's look, for example, at this scatter plot. What does this represent? Well, this is a scatter plot of SO4 on the x-axis, so sulfate, and sample elevation on the y-axis. Let's do one more. This plot right here, this gives you a scatter plot of chloride on the x-axis and sulfate on the y-axis. And then lastly, while we're at it, this scatter plot right here has chloride on the x-axis and sample elevation on the y-axis. What about the other scatter plots? Well, they have no new information. They have the same data, but just represented in a transposed way. What do I mean by that? Well, let's take this scatter plot, for example. This scatter plot will have SO4 on the y-axis and sample elevation on the x-axis. So it's actually the same plot, the same plot as this one. These two are the same, except the axes have been switched. X and y-axis have been switched. So typically when you observe a scatter matrix, you would look either above the diagonal or below the diagonal, and you would let the diagonal elements tell you what the labels for the x-axis are. Also, for those of you who remember the binomial coefficient, you will recognize that there are potentially a lot of scatter plots to make. So if you have n variables and you want to look at the association between any pair of those, then there will be n choose 2 scatter plots to make, and that is equal to n times n minus 1 divided by 2. So if you have 3 variables, then you have 3 scatter plots. That's fine. But if you have 5, then you already have 10 scatter plots to look at. That can become a bit cluttered. So scatter matrix is good if you have 3, maximum 4 variables. Beyond that, it's sometimes a bit doubtful if you'll get much information